Hi there. So I've been working on this project in which I've been building a Redis, something similar to Redis. And as you can see, I've created like basic servers and a client file. I'm basically using C to implement sockets and create the whole application. I've been following this build your X tutorial for this. This is basically my for my learning basically, right? So right now I am trying to implement AVL tree for the sorted sets, and so far I have wrote some code before starting recording this, and I now basically want to document this, and for that purpose only I'll learn the concept from the tutorial and try to implement those here. So as you can see, more or less, some things I've already written uh, for the wheel tree. From going forward, I'll try to record things while writing, but I'm not at the moment going to again write this. For context, let me show you what exactly are the AVL trees. AVL trees are basically binary search trees, which are self, which are balanced, right? So for newcomers who do not know what binary search tree is, it is basically a tree in which the left child is less than the parent, and parent is la parent is less than the right child, right? So it can, if I have to give an example, it would be, let's say 10 is my parent, and for 10 we have left child, how do I, left child this, and uh, this for the right child, and left child would be, let's say 8, and right child would be 12. So as you can see in this, in binary trees, the arrangement is the elements are arranged such that we can at any we can, let's say we have to search an element, let's say we have to search 12, and then we can start at 10, and since we are at 10 we know that the element that we need to search cannot be on the left side, is greater than the target is greater than the current node, so it has to be on the right side. This property is given by the binary search tree, which which helps to do these searches in logarithmic of n time, since we do not have to consider the half part of the tree, right? And one more thing, it has the in order of this binary search tree is generally a sorted array. The in in order type if we do the in order type in order trans what we say transition, we travel in order type in the tree, then we will get a sorted array. So this is the property of the binary search tree. Now, why one issue with the binary search tree is that it can be like there's a chance that in which all the elements are in a loop. It can be skewed basically. That will make it a linked list, right? For example, let's say in the above scenario itself, if we had 8 as the root, then the 10 would be its left child, right child, sorry, right child, and 12 would be the right child of the 10 itself. So as you can see, this now this has become a more or less a linked list, right? And this will make our search time logarithmic of n, worst case scenario. And in the above, and this is a balanced one, right? here the our search time will be logarithmic of n. Now, how A will come into the picture? AVL is a balancer. AVL is a balanced binary search tree. It makes sure that we get most of the always this kind of configuration, so that the search always stays logarithmic of n, and we do not get this skewed version. How do we get this? There is only one property that the AVL trees follow, is that at any given time, for a node, the difference in the height of left tree, oh sorry, height of left subtree minus height of right subtree, should, modulus of this, of course, modulus should always be less than 2, right? That means we can have this 7, we can have this, but we cannot have this. Got it? Like in this scenario, the height of the right subtree becomes twice the more than the right subtree. When this scenario occurs, we need to basically balance the tree such that we get a balanced tree. For that purpose, we use rotations. We will rotate at eight. We need to make some rotations, left and right rotations, and so that this can be transferred into, one thing we can do is we can take 8 as the root, right? And is right subtree, and in the right we can have 10, and in the right of 10 we can have 12, right? And here we can have 7, and then we can have 6. Now this is a balanced tree, as you can see. This is a balanced tree. Now this skewed problem has been resolved, right? Yeah. So to like make the balance, we basically made the 8, uh, the left subtree's root as the root of the overall tree, and uh, that made the complete BST balanced. Now what we did is, here is known as this is known as right rotation. Let me just get the tree right. This is known as right rotation. In right rotation, what we did is, basically we took the root, uh, like we basically took the root of the basically left child of the our, let's say this is our node. We took the left child and made this as a primary node and adjusted the tree for that. This is the right rotation. And in the left rotation, it is opposite of the right rotation, as the name suggests. We would have taken the right child and made that as a root, right? How we did it to achieve that? Let's say for right rotation, right, right rotation. In mean, what we did is we took we basically we basically took the left child, that is it, left child. We first of all take the right subtree of the left child. Here we didn't had any temp. Let's say temp with the variable and left child's. This would be left child's right. Okay, and this is temp, and we assign left child's right as is equal to our root. Root will be our left child's right since root is larger than the left. And then we assign the roots left temp to the roots left. That was left child's right subtree since is always greater than whatever there is in the left subtree. We have to assign it to the left. Similarly, in the right left rotation, we will take the temp right child's left, right, and and right child, assign the root to the left of the right child, since right child is always greater than the root. Anything in the right subtree is always greater than the root. And we what we do then, root assign temp to the roots right, since temp is always greater than anything in the right subtree is always greater than the root, so we had to assign it to the root. So these are the basic rotations that we can do to make the balances. Now we have scenarios, uh, s- unbalanced scenarios, right? Unbalance could be caused uh, in the left subtree. That is, left subtree has has more than one height than the right subtree, and in the left subtree itself, we can have imbalance on in left subtree's left child, right? In this scenario, we can simply do one right rotation, and and the tree will balance out. And if the right child is the one which is causing the imbalance, then we have to first left rotate the left subtree, right? And then do a right rotation at the root. Similarly, right rotation at the root, right? And in case the imbalance is due to the right subtree, if it is caused by the right child, then we do a left rotation to the root. And if the imbalance is due to the left child, then we first do the right rotation and then the left rotation. This way, we handle the imbalances in the AVL tree, right? So if we go to the code of the left rotation, you can see taking a right subtree, and inner tree is basically the right subtree's left part, uh, which would be, let's say this is the left tree, and it also had a left child, that would be 11. Just taking an example, right? So in this scenario, this is the inner tree I'm referring as. Then doing the same rotations that I did earlier, and then do an AVL update. I'll show you what AVL update is. Similarly, doing the right subtray, right left sorry, this was the left rotation. This is the right rotation. Both are done as per the pseudocode I showed you earlier. Then this is the condition which I showed you, like if the we have to fix the left subtree, if the imbalance is caused due to the left subtree, then if the height of the right is greater than the height of left, that is the right child is causing the issue, then we first do a left rotation of the left subtree. Node is our root and left is the left subtree, and then we basically do a right rotation for the overall node, and same for the right, vice versa for the right if the issue is in the right side. Let me show you the AVL update. This is basically doing we are maintaining the count and height of the left and right subtrees. Basically, each node. Uh, First, let me show you the AVL nodes definition. So in AVL node, I'm saving a parent, its left child and its right child, and its height for easier calculation, and the its size, right? So whenever we do an AVL update, let me show you AVL update. AVL update is we are basically updating this size and height of that particular node. That is the AVL update. And AVL height, these are the helper functions. AVL height and AVL count, they are basically returning these statements, these values of these where, uh, attributes, right? So yeah, that's it for this one. Uh, if you have any issue, you can drop a comment and I'll try to answer those. And for the next further, we can uh, in the next video basically. Yeah, thanks.